Okay, so we have this circuit, and you see there are no instructions, and basically what we would like to do is to simplify this circuit into its equivalent impedance, and then from the equivalent impedance we can get the current and also get the phasor diagram of the equivalent circuit. So the given quantities are a sinusoidal voltage of 10 volts operating at 2.5 kilohertz. You have two capacitors C1 and C2, and then three resistors R1, R2, R3, and R4. R4 and C2 are parallel to each other. R1, R2, R3 are in series, and they are also in series with C1. So the first thing that we need to do here to simplify this circuit is to get the equivalent circuit for the parallel R4 and C2 circuit elements, and then from there combine them with the C1, R1, R2, R3 to get the total equivalent impedance. Okay, so the first step that we're going to do is to determine the angular frequency. So the angular frequency in this case is 2 pi f, and f is 2.5 kilohertz, so that's 5,000 pi hertz, which is about 15.7 hertz or kilohertz. Okay, the next step is to combine these two parallel circuits, and what we want to do with that is to get the equivalent impedance, which we will call C1. So in this case, so combine C2 and R4 to get Z1. So to get Z1, we first need to get Y1, but to get Y1, we need to get its components, G1, the conductance, and the capacitive susceptance. So the conductance G4 is just the reciprocal 1 over R4, and the capacitive susceptance BC2 is just the reciprocal of 1 over XC2, which is just omega C2. So now we can solve for Y4, which is equal to G4 minus BL minus BC2 and J hat. Okay, this will then give us a value of 1.1 millisiemens plus 0.7 millisiemens J hat. Okay, now I used MATLAB in order to solve for these quantities so that it will become easier. The next step is to solve for Z4 or Z1, which is the reciprocal of Y4. Okay, now if you're not familiar with handling complex numbers, this is how you solve for it. Let's say we have a complex number which is equal to a times a cosine theta, because this is the real component, plus a sine theta, which is the imaginary component. Okay, and then we want to take the reciprocal of that number, which we equate to b, for example. What we're going to do then is write this down in the denominator. Okay, and then we multiply everything by 1, or a cosine theta minus a sine theta j divided by a cosine theta minus a sine theta j. Okay, the numerator becomes a cosine theta minus a sine theta j, everything divided by a squared cosine squared theta plus a squared sine squared theta. And it's a plus sign here because j squared, as we know, is -1. So we factor out the a in the denominator, a squared in the denominator. We're left with cosine squared theta plus sine squared theta, and that should be equal to 1. So the denominator is a squared, and then we simplify this as cosine theta over a minus sine theta over aj. Okay, now remember that a here is the amplitude. So just to be clear that that's the amplitude and not the phasor component, which means that this will give us, or you can compute manually using this equation or using this technique, or you can simply use MATLAB. So in MATLAB, Z1 will give us 627 ohms minus 421 ohms J hat. Okay, now that we've solved for Z1, okay, this is the equivalent circuit there. Next step will be to solve for R1, R2, and R3. So in that case, okay, that's step 2. Simplify R1, R2, and R3. So let's say that's R4. So R1 plus R2 plus R3 is equal to R4, and this will give us 2.68 kilo ohm. Okay, so we call this as our R4. Okay, next we combine this C1 and R4 to get the impedance Z2. Okay, and that's actually easily done. Okay, what we do is simply to write Z2 equal to 2.68 kilo ohms plus XC, which is 1 over omega C. So 1 over omega C J. Sorry, this should be minus, because recall the equation is Z2 plus, or Z2 is equal to R plus XL minus XC J hat. Okay, so this should have a minus sign. So Z2 for us will be equal to 2.68 kilo ohms minus 4.24 kilo ohms J hat. Okay, so now that we know Z1 and Z2, we can combine them to get the total impedance, or the equivalent impedance. So the equivalent impedance will be, we call Z, so Z1 plus Z2. Okay, and that's also easily done. We only add up the real numbers together and then the complex number, the imaginary numbers together, and what we get is 3.331 kilo ohm, then minus 4.67 kilo ohm J hat, and that's for Z. Okay, so we need to get the absolute value of Z, because we want to get that. Because we're going to use that value in order to solve for the current I. So this is 5.72 kilo ohms. How did we get this? 3.31 kilo ohms squared plus negative 4.67 kilo ohms squared, and you take the square root of that. Okay, so that's your Z. Okay, and for the phase angle, okay, Now remember that the phase angle is equal to tangent inverse of XL minus XC divided by R. Okay, this is our R and this is our XC. Okay, so that will give us a value of negative 54.7 degrees. Now that we have solved for this, we can now draw the phasor diagram. Okay, the phasor diagram for the impedance involves the real component, which is this value, the imaginary component, which is this value, and the amplitude, which is this value. Oh, a solution appeared. The magic of technology. Okay, so here we have the impedance phasor diagram. The x-axis is the real axis. As you can see, it's about 3.31 kilo ohms. Okay, so this is actually in units of ohms. And the y-axis is the reactive component, and it's about 4.67 kilo ohms. Okay, so this is in unit of ohm. Okay, you don't see that it's actually 3.31, so it's 3.5 here, and here it's 4.67, but it's supposed to be 4.67, but you see 4.5 here. And the reason for that is that in MATLAB I'm using a command called quiver, and quiver draws a vector, but it does not draw the whole magnitude of the vector. Because graphically you draw multiple vectors and you don't want all those vectors to touch from head to tail. So this is why the length of the arrow does not correspond to 3.31 or 4.67 as it should be, and that's only because MATLAB or the command quiver does not draw the arrow to its full magnitude. Okay, but you can check for yourself that the mathematical answer is correct. You can also see that the angle is negative 54.7 degrees, and it's negative because, again, the circuit is purely capacitive, and we expect the reactive component to be in the negative part. Okay, the magnitude of this green arrow is 5.72 kilo ohms. Okay, there's one more thing that we need to compute, and that is the current. The current we can easily get by dividing the voltage with the absolute value of the impedance. And the current here in this case will be V sub S divided by the absolute value of Z. So this is 10 volts divided by 5.72 kilo ohms, okay, which is about 1.7 milliamperes.